All right, welcome, and thanks again for joining us for section 1.2 notes. This is a slightly larger section. If you could see in this top right corner, we've got 16 slides to get through. We're going to be doing 8 of them as notes, and then we're going to be doing 8 of them as examples, just to give you an idea of what we're running into. So in section 1.2, what we're going to be talking about is functions. Now, a lot of this is going to be very explanation-based, and the actual work that goes into a lot of this is extremely easy work, but the concepts are extremely important as they sort of trail throughout the entire year. And I'll talk more about that when we get to those. So first, let's just define what is a function. Let's make sure I have a pen. There we go. So a function is a relation in which each item from one set is paired with only one item from the other set. So we didn't really start by talking about relations, but relations are really just any time that there's a relationship between two sets. A function takes it a couple steps further because what it says now is that it's a relation in which each item from one set is paired with only one item from the other set. And you'll sort of see this like graphically and in tables, and it'll make sort of more sense if you're struggling with visualizing that. Or a different way of saying that is a function f from a set A to a set B is a relation that assigns each element x in the set of A exactly one element y in the set of B. And really, just to summarize, that's really just saying that each x value can only have one y value. The set A is called the domain. That's our set of inputs, and that's usually our x values. The set B is our range. It's the set of outputs that you can get, which is usually our y values. You know, if you're thinking about a graph, that's what that's graphically talking about. Domain is talking about our x's, the possible ones that we can put into our equation. And the range is set B, those are our outputs. Those are the things that we can get. So one example of a function is just the time of day and temperature. So this obviously has a relationship. Each time of day has a temperature. There's some relationship going on there. But it's also unique in the sense that each hour can be assigned only one temperature. So at 1 p.m., it's 9 degrees Celsius. At 2 p.m., it's 13 degrees Celsius. Notice we couldn't have a single time of day, like at 4 p.m., it can't be both 15 degrees Celsius and 10 degrees Celsius. Now you could be saying like, oh, but like at 4:50, maybe it's warmer. But that's not 4 o'clock p.m. That's 4:50 p.m. So each individual time of day can only have one temperature. That makes it a function. So to talk about some of the characteristics of functions, we've got 4, and really it's the last 2 that are like the ones that sometimes come up as issues, and more so really just the last one. So first, each element of A must be matched with an element of B. So each element in the domain must match to an element in the range. Some elements of B may not be matched with any element of A. So we don't have to use all of our range. We don't have to use all of the elements in our output. Third, 2 or more elements of A may be matched with the same element of B. So again, if we're thinking about this in terms of like on a graph, X's and Y's, this is just saying that we can have 2 X values that give us the same Y value. That's perfectly okay. On the other hand, an element of A cannot be matched with two different elements of b. So we can have two x's that match to the same y, but we cannot have one x, one element of a, that matches to two different y values. And again, you'll see that graphically. It's actually something that you already know. You just haven't usually said it all like this in all these words. So we're going to test for a function here. We're going to do this one together. Does the following relation represent y as a function of x? So we have our input and our output. We have 2 and 11, 2 and 10, 3 and 8, 4 and 5, 5 and 1. Each element of x is being matched to an element of y, or each element of A is being matched to an element of B. Each input has an output. And we're looking to see, are there any issues here? Okay, 5 goes to 1, no big deal. 4 goes to 5, 3 goes to 8, 2 goes to 10, and 2 goes to 11. Well, this right here presents an issue. Because in this fourth characteristic, we said an element of A cannot be matched with two different elements of B. And here we have an element in our input, 2, that's being matched to two different outputs. So we would say that this is not a function because an element of A matches to two different elements of B. Again, it's actually not new. You've seen it before. You just haven't seen it necessarily written out like that. All right, so let's talk about things that are functions then, or function notation. So function notation is just a way of sort of noting that a relationship is a function, and it allows us to sort of explain a little bit more without actually writing anything more. So the function that multiplies a number by 2 then adds 7. So we're multiplying by 2 times some number, then adding 7. So we're used to seeing this as like y equals 2x plus 7, where x is the input, aka the domain, and y is the output, the range. So I'm going to put in an x value, and I'm going to get a resulting y value. This, just a hint, it is a function. Since this is a function, we can write it talking about something like f of x. Now, this is not pronounced fx. Please don't say fx. It's f of x, meaning the function dependent upon x. So if we wanted to write this as f of x, we'd just say f of x equals 2x plus 7. Look at that. All I did was replace y with f of x. That's function notation. Look at it. Easy. So then if I were asking, like, what is f of 3? This tells me a lot. It's telling me I'm substituting into the f function. It is a function in the first place. And the x value that I'm going to substitute in is 3. So I'm replacing x with 3, or substituting 3 in, and then just simplifying. 2 times 3 is 6, plus 7 is 13. I don't do anything with this 3 over here. That's just indicating what did I substitute in to get this output. F of 3 equals 13. All right, we're going to skip that next page of examples. We're going to skip that next slide of examples. We're going to talk a little bit about piecewise functions. So a piecewise function. Piecewise function are functions that combine two or more other functions on restricted domains. So a piecewise function is literally where you're saying, like, you're cutting up one piece of a function and then gluing it to another thing. So for instance, I'm like cutting up a linear function, a straight line, and then I'm gluing it to a piece of a parabola, and then I'm going to glue some other thing, I don't know, an exponential function at the end of that parabola. So you're just chopping things apart and putting them together. A nice example of a piecewise function that you've already seen is f of x equals the absolute value of x. So your absolute value function is a piecewise function? Because it has, if we're thinking about what does the absolute value function look like, looks like this. But it has a different equation to the left of 0 than it does to the right of 0. Notice these are both just straight lines, if I was better at art. So let's talk about to the left of 0. If x is less than 0, so here's my restriction on the domain, then the equation of this line is simply negative x. If x is greater than or equal to 0, so now if I'm looking at just the right side of this graph, this is just a regular increasing linear function, so it's just x. Here, talking about piecewise functions, this is my domain restriction. It's telling me where does this function exist. So negative x only exists to the left of 0, and here's negative x, and it stops once we get to x being 0. Once x is 0, then we have the equation that's just positive x. So now, everywhere to the right of 0, I just have positive x. We'll see more with piecewise functions. Particularly, they come up a lot in Chapter 11, which is what we end the year with. So exciting. All right, we're going to skip that next one. We'll do that in the examples video. Same thing with that next one. And we're going to skip ahead a little bit now. I skipped a little bit too far. So find the domain of a function. We're on the 12th slide here. Now, domain is one of the things that we use like all the time throughout the whole school year. And sometimes it just shows up in like one problem in a chapter, but in like a really cruel way. So we always need to keep in mind the domain of whatever we're working with. Most functions that we will encounter have a domain of all real numbers. Because usually, if let's say, for instance, that I'm working with something that's linear, we're in this chapter where we've been talking about linear things. If I'm working with something that's linear, I usually don't have any restriction on x. I'm just going to jump back a little bit. You don't have to. If I go all the way back here, when I have 2x plus 7, there is nothing that I cannot put in for x and get some value. I could put anything in there. And that's how a lot of the problems that we deal with are going to be. However, we will have things that do have some restrictions. And namely, we have two different functions that we need to be concerned with. The first one is a rational function, something like f of x equals 1 over x. So this is a rational function. And there's a domain restriction because we cannot have a denominator of 0. So I couldn't have 0 in that denominator, meaning there would be some restriction. Our second one is a square root function, something like g of x is equal to the square root of x. So the issue with that one is that we can't have a negative underneath that radical. So when we talk about the domains of f and g then, f being the rational function, g being the square root function, we're going to do two different things here. One for f. So if we're looking at f of x equals 1 over x, again, the domain restriction that we have here is that x cannot be equal to 0. So as we sort of progress throughout the year, we'll talk about different notations for this. This is one that's pretty common for rational functions. And it's usually something that we would just jot down on the side of a rational function. It's not how we will usually answer the question, though. Usually what you're going to be required to do is interval notation. Interval notation is where you're stating the domain and saying what is all the things that do work. So the only thing that doesn't work is 0, which means I can go all the way starting at negative infinity up until 0. And then I put a parentheses. This parentheses means that 0 is not included in the set of things that work. I put a little union with, and then I'm starting at 0 again. This parentheses means that 0 is not included up until positive infinity. When I read this now, it essentially is saying you start at negative infinity, you go to 0, and then you don't include 0, and you include whatever is larger than 0, 0.000000001, and even smaller. This says the only thing from negative infinity to positive infinity that cannot be used is 0. All right, looking at our other function, g of x, we have g of x is equal to the square root of x. Our domain here is a little bit different because it's not a single value that needs to be restricted. It's an entire interval of things. Like we can't have anything negative underneath this square root. So our domain is that x must be greater than 0 or equal to 0. I can take the square root of 0. Again, if we want interval notation, we are including 0 here. So because I'm including 0, I'm not going to put a parentheses. I'm going to put a bracket, and I'm going to start it at 0. I'm not dealing with the negative infinity up until, because I can't use anything that's negative. This is going to positive infinity. And again, when I read this, this says the only x values that I can use are starting at and including 0 and going up to positive infinity. All right, well, skip those next 2 slides. We'll do those in the examples. And then this is the last one that we're going to do here in the notes, evaluating a difference quotient. Now, there's no notes that go alongside a difference quotient. It's just going to be examples of it. And we're going to do it now. You'll see it a little bit throughout like the next, I don't know, maybe 2 chapters, and then here and there. And then chapter 11, it becomes super, super important. Again, chapter 11 is what we do all the way in May. But it's really like your introduction to calculus. So talking about a difference quotient, they can be a little bit messy at times. Make sure you're following along. Evaluating a difference quotient. So here, this is your equation for the difference quotient. F of x plus c minus f of x all over c, such that c cannot be equal to 0. Again, rational function. And it tells us we're going to use the equation f of x equals 3x. So this first part, f of x plus c, all that is saying is substitute parentheses x plus c in for x. So I go to my original equation, I replace x with x plus c. Anywhere that it showed up. In this case, it only shows up this one time. So there, that's what I did. I did f of x plus c. I replaced x with x plus c. Now, subtract the original function. So I'm going to subtract, and I always put the original function in brackets. And you could put it in parentheses. You cannot put it in parentheses if you want, but it's just important to remember that this subtraction is going to be distributed to every term in the original function. In this case, there's only one. This is all over c. And then I just simplify this. So I'm going to distribute this 3, and I get 3x plus 3c. And I'll distribute this negative, minus 3x all over c. Notice here the 3x minus 3x, that should happen. If it doesn't happen, if this original function doesn't cancel off, you've done something wrong. Go back, find it, change it. Equals 3c over c. And now I'm able to cancel off these c's so that I don't have to worry as much about that c cannot be equal to 0. And we just get 3. So when we evaluated the difference quotient of 3x, we got 3. All right, that's it that we're covering for the notes. Again, there is a relatively long optional video that's just all the examples. I recommend that you really do pay attention to it, work through it, go through at least a little bit of it. Some of it is easier stuff, some of it is tougher stuff, especially this difference quotient thing. Otherwise, make sure that you go that you guys go back, jot down any questions that you have, make sure that you bring them for class tomorrow. Thank you.